Welcome to this ATA Insights webinar. Thank you for your ongoing interest and support of our webinar program. Today's session will begin in 2 minutes. ATA Insights Webinars is an online platform for the dissemination of professional renewable energy knowledge across international borders. Our aim is to democratize access to information, for innovation to spread faster, and to make the industry more competitive. And we do this through our online sessions, open to all our members. Every year we do more than 100 sessions with over 250 speakers, 50,000 attendees from more than 50 countries. To participate in the session today, use the chat on the right-hand side to introduce yourself, your company, and where you're joining from. Under the screen, you will find the Q&A box, where you can send your questions for the speakers. We will get to as many as we can today. We're recording this session, and we will send you a link to the materials in a few days. Please consider supporting our content creation for the webinar program. Contact us on the email on screen. Well, welcome everyone to this online session in which we are going to focus on how to maximize the value of your solar assets using energy storage technology. Energy storage is something that we talk a lot about in these webinars, in events that we do. So you're not going to be probably new to this topic. We've discussed this quite a lot. However, usually we talk about it from the technical perspective. And at the end of the day, any technical talk that we have has a business component that we must consider and that is very important in what we do. So it's not so much about understanding the technology itself, which is also important, but it's about understanding what it means for your business and how you can deploy it in a way that is commercially astute, so to speak. And this is what we're discussing here today. And I think it's very important because as more and more renewable assets join the grid, as you know, and as curtailment levels very slowly but very surely are pushing up through most of the grids around the world, and we're seeing this increasingly in countries in Europe, for example, energy storage is going to become the key tool that you're going to be using in order to make sure that your project stays competitive and commercial. But don't you worry, because I am going to be your moderator today, but you're not going to hear from me about this. We actually have three experts in this topic who are going to be talking to you about this specifically. And I have the pleasure of introducing them now so that you can get to know them a little better. So please, can I ask first if I can ask Wilhelm to introduce yourself?
Yes, of course, Dylan. Thank you very much for the introduction. My name is Wilhelm Van Butselaar. I'm working as area manager for energy storage and optimization at Butselaar. I'm with Butselaar for about 5 years now. And after I studied renewables, actually, at university already based on batteries and off-grid systems, I spent 5 years working in Germany for a large inverter manufacturer. And later about 10 years in Australia, and then the South Pacific, and have been in touch and working in Southeast Asia for about 13 years. Some of these times are overlapping, of course. And all that time I've been working with renewable energies based on batteries for grid connection, but also for off-grid. And that's why I'm here today to talk a little bit about the technical side of DC coupled systems, just evaluating a little bit not only what the advantages are, but also what to take care for here. So I believe this is going to be a very interesting and exciting discussion.
Thank you very much, Wilhelm. What an interesting set of experiences you have there. I'm sure we're going to later learn a great deal from you. Next, I'd like to ask Sherif to please introduce yourself. Also, Sherif is someone that is pretty well known in the energy storage space.
Appreciate it, Dylan, and like always, it's a pleasure doing these webinars with you and ATA Insights. So thank you for that. So my name is Sherif Abdelrazek. I'm Director of Renewables Engineering, focused on energy storage and microgrids at Duke Energy. My team provides technical support to design, develop, and execute grid-tied distribution and transmission tied energy storage, microgrid, and solar plus storage projects. Between research and actual engineering work, I've been working on in the renewables field for about 10 years or so. Learned quite a bit. So always excited to do these webinars and just converse with my fellow panelists here and understand where the pain points on the industry is and also share our experience. So again, thanks for having me.
Thank you very much for sharing your experience, Sherif. Next, I'd like to introduce John. So if you could please tell us a little bit about you.
Good morning, everyone. John O'Brien from Private Energy Partners, which is a part of the Quinnbrook Infrastructure Partners fund family. Specifically, what I do is I help integrate storage and storage components across the platform that Quinnbrook has. So helping out with the glide path team, Habitat software, which is our energy optimization, helping both of those two as they grow in the US. We have a company called Primergy, which is operating or developing and building the largest solar plus storage project in America right now. They have a fairly developed team, so I don't help too much there, but there's going to be a lot of growth inside of Quinnbrook with the belief that storage will be a component of everything we do to some degree or another going forward. Prior to joining Quinnbrook about 9 months ago, I spent the previous 14 years at Siemens Financial Services doing project financing across a variety of thermal and renewable projects, and had a particular focus the last 5 years on learning and financing kind of the first standalone storage projects here in the United States.
Thank you very much, John. So we're covering all the bases, guys. As you can see, it is very important that you start thinking strategically about what storage means for you, because I mean, I'm sure it's not the only reason to have storage, but the curtailment that's going to come in the next few months and years, depending on what market you're in, is definitely something that you need to look at and be prepared well in advance. So before we go with the presentations, and this will be a very simple webinar, we're going to have presentations in the same order that you heard the introductions from the speakers, and then we'll take questions at the very end of the webinar. I'm going to give you just a few housekeeping rules, or housekeeping instructions. One, please introduce yourself using the chat. We love to see who's there and where you're joining from. A few of you have already done it, but please don't be shy and tell us your name, your company, where you're joining from. We love to see that there's so much international people connected here usually. So thank you very much for your questions. However, and the questions will be taken at the end with the time that we have available. Please use the Q&A box at the bottom of the screen. Okay, we're going to take it there. And it just makes it so much easier for us to manage them and to be able to get to as many as possible. For the people that you're in YouTube, please, for the YouTube channel, just use the chat to send your questions. And then my colleague Lucia, who's actually in the back there in the tech desk, she was going to put it in here for us to see. And remind you just the last thing is that we are recording this session. So it's going to be available. You can watch it again. You can see the materials. So don't worry, because you're going to have the option to share it with your colleagues and get familiarized with it. So without further ado, I'd just like to ask Wilhelm, please, if you can prepare your presentation so that we can start. And it's amazing. See how many more people we have now here, people from Latin America to Africa, everywhere in Europe. Perfect. Wilhelm, can you put that into a bigger screen? If you click there, you should be okay. Okay, let's see. Are you okay, Wilhelm? I'm not sure if you can hear me. Oh, there. We cannot hear you, okay? So can you unmute yourself? It's at the top. Oh, there we go. Perfect. Yes.
One taskbar was blocking the other one. All right. Okay. Thank you very much. So as we said before, this is a quite technical topic when we talk about DC coupled systems and talking about the advantages and also challenges. So this topic can be talked about for a whole day, for another ATA webinar, which takes about 8 hours if you want. If you would do that, so this can only be in a nutshell, in a 10-minute presentation, what DC coupled systems are about. Just before that, just one slide about what we've done so far globally in terms of storage. We are now at about 2.6 gigawatts and 6 gigawatt hours around the world, installed in all those 3 different regions. That's how we divide the world a little bit. And in the US, it has started to become very successful with the storage years ago already. In Europe, it has been developed in Germany, in the UK, but also you can see that in the middle of the Atlantic Ocean, there's installations. So talking about battery-based mini grids, just what I've mentioned before, that has been realized there. And Australia, Philippines, in Singapore, but also in Taiwan, there is quite some activity. And the reason why I've started to talk about the US, you will see later actually an example of a DC coupled system in the US we have realized that. So just to get everyone on the same page, what are solar plus storage systems, or in that case, DC coupled systems? I've chosen this picture because on top in the horizontal line, you see actually the structure of a normal PV system. So on the left, the solar panel sending the energy through the inverter to the grid, converting from DC to AC. And in what we call AC coupled systems, the energy system, the battery storage system would be connected separately to the medium voltage level. But in this case, in DC coupled systems, the battery is hooked up on the same DC side like the solar panels, which is a complete different topology, and we will see a little bit later why this has been done. The way we are looking at DC coupled systems is limited to battery plus storage only. So at the moment, we are not coupling anything else on the DC side. And again, for use case reasons, we will see a little bit later, that makes a lot of sense. So just as a comparison here, on top, we see the usual AC coupled systems. As I said before, the PV system is separately connected to the medium voltage level through a low voltage to medium voltage transformer. And the same goes for the battery. So they are, so to speak, modular blocks being separately connected. If you look at the bottom at the DC coupled system, again, you see how the battery is connected directly to the solar panels and together to the inverter on the DC side. Now, talking about the first and main advantage here, it's all about conversion losses. So this is what the DC coupled system wants to reduce. So first of all, here in an AC coupled system, we are looking here at the process of charging and then discharging the battery. So the energy from the solar panels would go via the inverters, losing about 2% of energy. And again, this is very high level. This is simplified. Can be a little bit more, can be a little bit less. Then it would lose another 1% via the transformer. Then in order to further go to the batteries, it would lose another percent via the second transformer, and then another 2% via the battery PCS. Now the energy is being stored. Now if we go back, because we need to send that energy then discharging into the grid, again, about 2% via the inverter, about 1% via the transformer. So you see on top right, we would lose about 9%. It sounds a lot, but it's actually quite standard for that whole process to have those conversion losses. So let's just keep the 9% in mind. One reason why I'm showing you the bottom right picture is already the other main advantage of DC coupled systems. So you would usually size your PV panels behind the inverters in their own power a little bit bigger than the inverter itself. So that means during noon, when the bell curve reaches its peak, as you can see here, there might be what we call a clipping effect. And that means that not all the energy can go through the inverter because the inverter's power is smaller. So that is very normal for AC coupled systems. We will see a little bit later how we can actually capture that clip energy with a DC coupled system. Now, let's look at that DC coupled system. Again, we are looking at the process of producing energy, sending it to the battery, and from the battery back to the grid. So the DC-DC converter has in average a loss of about 1.5%, and that's all. That's where we are already in the battery, right? So we only have a DC-DC converter in between. Now we have to discharge, lose another 1.5%, and then go via the common inverter, which in that case is a PV inverter, to the grid, losing another 1% via the transformer, and that's it. So it's about 6%. So if we compare those two processes, the gain we have here in DC coupled system is about 3%. Again, can be a little bit more, can be a little bit less, but that's quite a lot if you look into business cases, and you would have actually a total of 3% more energy. So this is the one example. Now, talking again about the clipping effect. So what we want is to capture the orange area. And because the solar panels are not limited in their power anymore by the inverter, so we don't have to squeeze everything through the inverter, we can store the energy directly into the batteries. So the full bell curve could theoretically go into the batteries without electricity. So that's the second large advantage here. Talking about the use cases, three main use cases are targeted here. One is capacity firming. So that means if you are, for example, in a PPA contract and you are committing to supply a certain power from during a certain time and day, which can be, let's say, I don't know, 50 megawatts from 9 in the morning until 5 in the evening, flat. So that's what you would do usually with a PV plus storage system. Another one is energy shifting or time shifting, which you see on the top right picture, which means charging during daytime and then use the energy in the evening. And lastly, we talk about power ramp rate controls, which is there to reduce the unwanted effects of intermittency on the grid, which means that a dark black cloud would cover the solar system and suddenly go away, then the power ramps up very, very quickly. We don't really want that. We want to slow that down. And also when the black cloud comes and covers the solar system, then the power shouldn't drop immediately. So that should be delayed. And that's what we call reducing ramps, which is visible in the green line here. And then we have so-called secondary use cases. So if we have been looking into those with solar, and then we can say once those use cases have been established, then the same system can also realize more than just one use case. So we are talking about stacked revenue streams. And that can be, for example, frequency regulation and voltage support. So not primary, but once the system is there, these use cases can be realized. This is an example of our system in the US. I mentioned that before, it's in Georgia. So that system is the battery size of about 40 megawatt, 80 megawatt hours connected to about 200 megawatt of solar. And the targets here were what I've mentioned before: improved system efficiency, lower balance of plant costs, because now we are talking about combined TCS of solar and storage. So the number of TCS can be slightly lower. And again, capturing the grid solar energy here. Quickly, a few words about the EMS. Now, we're talking about a different topology here, and very quickly it could come to mind that maybe we need a different software here because it is a different topology. But the answer is clearly no. Existing energy management systems like our GEMS can handle that easily because the overall structure and how the systems work are still the same. You got your combination of, in that case, energy, storage, and solar on the left. You still have to use your power plant controller and the grid controller in that case in order to, on the right-hand side, have an optimized flexible generation. So not much of a change here. And I really would like to minimize the effect usually that happens with new topologies. People get a little scared because it's something they don't know yet. So it's very quickly and easily described as complex, but it's actually not. It's no magic. It's quite easy. And talking about that and software, there is one other thing I would like to mention here. That system in the US, which by the way has been realized with RWE, it is optimizing the efficiency and capturing that curtailed or clipped energy. But it also has one part of the software which we call actually a PPA optimizer. It uses internal forecasting for weather. It uses data, it learns from data that it has seen in the past. And with that, it is actually forecasting a certain behavior of the overall system and what energy will be available in the next hour or even tomorrow to be supplied to the grid, so that commitments can be done as accurate as possible. So lastly, and this is a table with a lot of text, I will just quickly go through those points here which are in bold. If we compare those two systems, certainly there are advantages in both. So if we talk about the design considerations, AC coupled systems are a little bit easier to design than DC coupled systems. However, the design of DC coupled systems enables to reduce CapEx. Bankability, AC coupled systems are known for the last 10, 15 years in a larger scale. So that is easier and accepted by both banks and insurances. But once DC coupled systems have been proven to work, have been installed a little bit more around the world, then we believe that will become very equal to each other. If we talk about the use case and the revenues, we are talking at AC coupled systems a lot about revenue stacking. So use many more use cases in one system because batteries in solar in that case would be independent. But the DC coupled systems, as mentioned before, offers to even capture clipped energy, which is helping the business case quite a lot. And lastly, interconnection and approvals here. Same like the very first point. AC coupled systems are easier to get approval because it has been proven that the systems work, it has been accepted, and systems are up and running in gigawatts around the world. So for DC coupled systems, that's rather a little unclear. In a lot of established markets, those guidelines for DC coupled systems are yet to be established. All right, so that was in a nutshell DC coupled systems and what to look out for. Again, there is a lot more to talk about it, especially when it comes to engineering, to performance guarantees and all those topics. But hey, maybe there's another session anytime soon to talk about it. Thanks, Belen.
Thank you very much, Wilhelm. Considering that you needed 8 hours to talk about this, you've done a remarkable job getting to the gist of the issue. So thank you very much. And I do understand that, especially for someone who knows so much about the topic like you guys, it's really, really hard to make it really synthesize. But the way I look at this is, one, we give information to people, so the people in the audience are learning, but also they know who are the experts that can resolve these issues and can contact them in their time, whenever you have questions specific. So Wilhelm is there at your disposal if you want to reach out to him. These details are in the presentation. So thank you very much for that. Next, I'd like to ask Sherif to please show your presentation and go for it.
Sure. Can everyone see my screen?
Yes, perfect. Yeah, we can see AC coupled, DC coupled right away, which is a topic that everyone loves, by the way. So go for it.
All right. Great. Right. Well, what I'll go through here is I'm going to try to provide an overview of what we have learned at Duke Energy, working with a lot of major integrators like Wärtsilä and many others, several types of projects, distribution tied, transmission tied, DC coupled solar plus storage, AC coupled. We've done a good deal of each. So what I'm going to try to do here is go over the architectures that we have found out there with OEM equipment and just provide a summary of the pros and cons of each, and then get a little bit into the weeds on a point that Wilhelm went over, right? Clipped energy capture. right? So really, how much clipped energy do you stand to really capture with a DC coupled battery system, right? And like many things in the battery world, the answer is it depends. So naturally, I have some curves to go over. All right, so starting off with the architectures, right? So we always talk about AC coupled or DC coupled, but what often gets missed is that really there are subtypes, right? It's not just two. So I tried to summarize the types of AC coupled systems that are out there and the types of DC coupled systems that are out there. Starting off with AC coupled, this first one here is low voltage coupled. And what you have is basically the solar connected to an inverter, and then the battery connected also to a bidirectional inverter and coupled on the low voltage side, low voltage AC side, right? And then using a common PCS transformer for both. This is advantageous a bit from slightly improved efficiency versus this other one for charging the battery from the solar, since you don't have to go through like two transformers to get the energy from the solar to the battery and then back to the grid, but also not as efficient as DC coupled systems. There are a number of manufacturers out there that use this architecture, but they will sell you like these two inverters just in one box, for lack of a better term. The only thing that, you know, from the inside of that box, it's just two different inverters, and they'll have multiple stacks of inverters, and you'll be able to connect multiple solar arrays and multiple battery arrays as well. But at the end, you use a common medium voltage transformer. Now, the other type here, medium voltage coupled, which is, I think, what Wilhelm had in his slide. This is kind of like having two entirely separate facilities, like solar connected to the inverter, connected to a PCS transformer, and then coupled at the medium voltage level with the battery through a medium voltage, through a bidirectional inverter and a medium voltage transformer. All right, now going to DC coupled, two types, one called solar charging. And as the name implies, you're only able to charge the battery from the solar. This is, I guess, more common with retrofit projects because you already have the solar facility kind of built, and then you're adding batteries to it. So this inverter, for the most part, is unidirectional. So you can't charge the battery from the grid, which limits your ability to perform ancillary services later in the day when the sun's not shining, when the capacity of this inverter is not being used by the solar. We actually did a retrofit in Florida with SMA inverters, and they were their Sunny Central series, just solar inverters, and with a simple firmware upgrade, they were able to allow the solar inverter to operate in bidirectional mode. So that was one retrofit project that allowed charging from the grid, which kind of makes it this type. Not all OEMs make it that simple to turn a solar inverter to a bidirectional energy storage inverter, but there are some out there that do. This kind of second type of DC coupled systems, like we discussed, exactly like this one. The only difference is this inverter is bidirectional. So in addition to being able to charge from the solar at the very high efficiency and capturing clipped energy, you can also charge from the grid to get ready for an arbitrage schedule or time of use, advantageous times of use rates, or participate in a market service. So bringing all that in, just put a quick kind of just, there's a multitude of factors to compare, but I tried to kind of summarize the most important points, right? So starting off with, the first characteristic here, PV to battery charging efficiency. And by the way, I bucketed AC coupled in as one here, but I split up DC coupled as two. But in general, for AC coupled systems, the efficiency of solar energy to battery charging is the lowest among the types that are here. How much lower? That is something that Wilhelm went over. So I agree with this summary. You're looking at around 9% or so kind of losses, and 6% in losses with a DC coupled system. But then the question becomes, right, should I just look at that? Should that be my my only metric? Well, no, because you have to start with thinking about the use case. What are you installing this system for? How much really clipped energy are you standing to capture? Are you only going to capture and charge energy that would be otherwise clipped by the solar, or will you charge more energy that would have just went through the inverter and onto the grid? So the rates that you have, your PPA, and whether it's time-based or just common rates throughout the day, makes a huge difference on how you make that selection. Next point here, control complexity. Now, AC coupled, very little complexity. It's almost like you're building two separate facilities, very well established in the industry, not much or not many complications there. Now, DC coupled, right? No shortage of complexity. Just on the control complexity side, it's not always very straightforward to get the DC-DC converter and the inverter to work together in a nice fashion. We've, at Duke Energy, we focused on having the OEM for the inverter be the same as the OEM for the DC-DC converter, so we can try to minimize that control complexity, and it has to a great degree, but still it's not as smooth as a lot of people would think. And you kind of, when you go to the flexible charging architecture, it even becomes more complex, because now you've just added another layer or another control mode to actually charge from the grid to the battery. So that's one side of it. The other side, right? Let's all remember, PV systems are in the US. I'm not entirely sure about Europe, but in the US, solar systems are either negative grounded or positive grounded. Battery systems are floating on the DC side, right? So when you connect the DC-DC converter, right, that is not galvanically isolated, when you connect a floating system to a negative or positive grounded system through a non-galvanically isolated a DC-DC converter, right, you get common mode voltage. So you have to check with your battery OEM whether it can take on that common mode voltage that will result. We checked with one OEM, and we're commissioning that project. It worked out, but this is just an additional layer that you have to make sure that your battery OEM is comfortable with. Right. So the next kind of feature here, energy storage grid ancillary services capability. So for each of these architectures, what kind of capability do you have to provide grid ancillary services with your battery, right? Here, AC coupled high, you're not limited by any inverter capacity. You have the full power and energy capacity of your battery system at your disposal. At your disposal, no issues there. DC coupled solar charging, which is extremely hard to say. You have much less flexibility because you're only charging from solar when it's available, right? And let's remember, the sun is not always shining, so you have to look at, your irradiance for that region, right? So the least flexibility for ancillary services in this architecture. Now, DC coupled systems with flexible charging, in other words, being able to charge from the grid, I think this gives you medium capability to provide grid ancillary services. And the only reason for that is, let's remember, this inverter is usually sized to this even much, as you know, much less than the solar capacity. So most of the time when the sun is shining, right, its capacity is being used to kind of to push out the solar power. So you can't use the battery at that time for grid ancillary services. It's one or the other. That's why it's a medium, gives you a medium capability to provide grid ancillary services. All right, so taking all these points into account, right, I tried to put together a primary use for each of these architectures, right? And this is what I came up with. For AC coupled systems, you should use this architecture if your primary goal is to provide grid ancillary services and you don't see much value in capturing clipped energy from solar, or even shifting solar energy. So if you have a PPA with just energy revenue being common, not changing over the day, there's absolutely no reason in my mind to be DC coupled unless you have an extremely high solar DC to AC ratio and you're just going to produce just massive more amount of energy from your solar by capturing it. And that's what the next slide is going to go over. DC coupled solar charging. Now, this is if your primary use case is to increase your solar facilities production. Let's just say you have an awesome rate from 10 years ago, and you have a high DC to AC ratio solar facility, and you're going to retrofit it. Yeah, this may be worth it. So probably think about this architecture if your primary goal is PV clipped energy capture. Now, DC coupled flexible charging, I mean, it's flexible as the name implies. It could be used for both, but you really want to look at the cost of it and your option and what kind of revenue you're going to get from capturing that extra clipped energy, and the less revenue you're going to get from grid ancillary services. So really, what the question of which is best, none of them are best. It's what is suitable for your specific case. So that's what I try to put together here. What would be suitable for what case? Now, we talked a lot about, all right, how much energy are you going to capture from the PV clipped energy that would be otherwise clipped by the inverters, and we've determined that that's a determining factor in which architecture to choose. So really, when you DC couple, right, a battery to a solar system, how much extra energy are you actually going to capture from the solar? Now, these two charts, right, one is for a 2-hour battery system that is DC coupled, and the other is for a 4-hour battery system that is also DC coupled, right? On the x-axis here, you have the solar DC-AC ratio, right? It ranges, from 1.3 all the way up. Now I've seen facilities go up to 2. And it's really, just a financial optimization, a function of how expensive the solar modules are compared to the inverters. So it's a very well-known and established solar optimization. And on the y-axis here, you have the energy production increase. So how much like extra energy are you actually getting from the solar by capturing that clipped energy, right? Now, all of these results are based on Florida. So it varies based on the irradiance of your region, but this is just meant for, as an example. So as you can see here, these different lines are for different percentages of the solar inverter capacity. So going all the way from 0, 20%, all the way to 120% of your solar inverter capacity, for the energy storage system capacity being this percentage of your solar inverter capacity. So it shows you kind of exactly how much extra energy you're standing to get. So for example, for this gray line, right, 40%, right? So if you have like 100 megawatt solar inverter, you have 40 megawatts energy storage. Since this is 2 hours, that's 80 megawatt hours. You're only getting 5% extra energy from the solar, right? But if the DC-AC ratio of the solar facility is higher, you stand to get about 7.5%. And of course, it changes as you increase the battery power capacity here. But on both the x-axis and also the power capacity of the battery system, you start to get diminishing returns as you go higher, both like this and you also like this, right? So you're always wanting to be at kind of the inflection point. Same thing with a 4-hour system, right? With, at Duke Energy, we had a lot of projects at 1.8, for example. So in Florida, for 40% of your solar inverter capacity, or a little over kind of 10% extra solar energy. So yeah, it just gives you kind of an order of magnitude, what you stand to gain. And as you can see, if you're, in my humble opinion, if you're kind of less than 1.5 DC-AC ratio, or even less than 1.4, the case for DC coupled is heavily in question, especially if you don't have like time of use rates, right? This is assuming like a constant PPA price, right? But if you have a higher DC-AC ratio, you stand to get a lot of more energy from your facility. Right, that I think is it. There's a lot more to mention, but I want to be respectful of folks' time here, so I'll pass it back over.
Thank you, Sherif. You're trying to put like a little bit of a formula or like share some light over the complexity of these calculations. And in the end, I think I've never really been in a webinar where we're like, okay, this is the clear answer. Thank you very much. It's always like, what's the right answer for you? So you guys get out the calculators. You're going to need them. All right. Thank you very much. Okay. So next, John, if I just allow you to go in, and we do have some questions. So we'll try to get to them as soon as we're done. And I can see that already some of them have been answered. So thank you very much, Wilhelm. And also if you see some that you want to go answering, Sherif, you go ahead. John, if you can put your presentation on.
Yeah, I don't have a presentation because it's not as
sorry.
detailed and technical as the previous two. It's a little bit more of a, I'm just not as smart as the previous two presenters. So a little example of kind of where I wanted to go was, what makes more of the commercial sense on a lot of these projects and decisions being made. So I want to touch on kind of what we've seen so far and what's been in the market. And to date, it's overwhelmingly been AC coupled solar plus storage, with some DC certainly growing a lot recently. Just not a lot of megawatts in the ground that is DC coupled. And I think A lot of reasons for that, but I think one, as was pointed out, the lack of complexity with AC coupled is certainly kind of where people wanted to go in the beginning. Just understanding how to do it without screwing up the technical side, I think was certainly a consideration. Something else is, if your project was being retrofitted or even kind of under construction at the time, it's sometimes hard to locate a suitable place to put a DC coupled, and it's just easier to put in, as I think Sherif said, just an entirely different power plant in under the same guise of a project that was just easier to drop in and operate that way. Certainly, a lot of the newer projects that were developed once solar plus storage have really taken off are going to be DC coupled for a lot of the reasons, technically, efficiency wise and cost wise. So we're certainly seeing that growing. Our Gemini project in Nevada is a DC coupled project, but just glancing back at kind of the IE report, it did make a lot of comments about how there just aren't a lot of DC coupled projects in the ground. So just a lot of AC. And again, I think that's a lot because of, people not comfortable with the complexity on kind of the first set of projects, but then also, retrofitting it back into kind of an envelope, a footprint that had already been really accounted for storage, for a solar only type project. So, but certainly a lot of DC going forward. Kind of the contractual and the revenue cases, and I think Sherif touched on that a bit. To date, especially in the U.S., there's the ITC associated with storage, and that required a certain amount of charging directly provable from that renewable source in order to claim the ITC. So, I think a lot of the use cases to date have been fairly limited. That said, I think you can take a look at a lot of the contracts themselves have written into it that, your battery will have some availability, your battery, there's some time of use rates, certain things that require you to be, cited and make it interesting to put in some solar plus storage. Again, tying it back to the AC DC coupled, a lot of the thought is, if we have a short duration type contract, what am I going to do with the battery after 5 years when I no longer have the requirement for charging directly from the solar project? Or, if my contract is 5 to maybe 7 years long as a CNI, what am I going to do with the battery, right? If my project requires, if my offtake requires that type of storage, for either for a time of use or for an overall capacity number, or whether it's pricing or a fixed set of megawatts, and then that PPA disappears after 7 years, what are you going to do with the battery? And maybe the best use case is not for a time shift in that location, but for something else. And having an AC coupled project makes more sense. Whereas if you have a more traditional PPA or a longer duration PPA that goes up to 15 to 20 years, DC coupled makes a lot more sense because your battery is going to be tied up by the contract for that kind of length of time. Financing wise, I don't think there's been a real distinction drawn between AC and DC coupled. And for that matter, I don't know if there's a huge distinction being drawn right now between a solar project and a solar plus storage project. I think the financial markets have been kind of taking the batteries, especially if they're kind of a top tier battery, top tier integrator, top tier developer, that your storage project, your solar plus storage project is really akin to that of a solar project. So that's something that did kind of surprise me back in the days of when I was in project finance, how quickly things accelerated from really from batteries being a new and lightly understood technology to being almost accepted like solar, which has been around for a really long time, and we understand all the peculiarities of solar and the degradation cycle, and there's no augmentation. Whereas with the contracts, now with the solar plus storage, it literally is going to be almost indistinguishable from a contracted solar project. So to me, the only difference in the way the financial markets will treat it is how much revenue are you attributing to the battery to kind of a market that isn't known. So, you know, straight PPA project, I don't think there's any distinguishable difference. You have a project that has some revenue, let's just say like a 3-year hedge, and you need the battery to maximize the hedge, but then, you know, years 3 through 5, you're fully merchant, right? I think that's where the markets draw the line. But if it's a straight contracted project, I don't think that there's, you know, a real thought being given to, unfortunately, batteries and the different risks associated with it amounting to, you know, a little bit of a bump in terms of a, you know, technology premium. Finally, just wanted to touch on kind of the new IRA, and that kind of takes a lot of what I said in the first and when it happened earlier, and kind of shakes it up a bit. What it does, since it removes the charging requirements for the battery, it kind of opens up your mind and your developer's mind in terms of where do I actually want to put this battery? What is the best use and the best location? And there'll be ways around it, you know, financially and structurally, you know, ownership wise. But in many cases, the best use for the battery may not actually be at the solar project site, but it may be somewhere else along the distribution grid line, or maybe on another side of a congestion point, just so you can maximize, you know, your overall project revenue. So, you know, you may sacrifice some solar project revenue for increased revenue by using the battery at a different location. And that could also help satisfy certain requirements under your contract, especially as kind of basis risk grows. And basis risk is really the difference between where in a competitive market where you sell the project, where you sell into the grid and the price the project gets, and where your contract is settled. So, you know, that's a particular interest in certain areas like Texas and California and here in the United States, because a lot of the renewable energy projects end up getting clustered and there just isn't enough line space to get the project from, you know, kind of the rural areas to the urban centers. And there'll eventually be a point where that grid can't handle all the power moving through. And that's where the price, you know, the price may be much lower where you're selling versus where, you know, you're saying you're delivering it to, and that difference is just a loss to the project. And if you have a battery in a right location, you may minimize that loss, especially if you fear that, you know, that loss is going to be growing. So, you know, I think the ITC, the standalone for the storage kind of opens things up for solar plus storage. So that actually be co-located. So, you know, solar plus storage may be more, you know, maybe deemed more hybrid than co-located. So I think those are all kind of interesting things going on in the United States. You know, other markets globally that are more bilateral, you know, clearly pairing the two projects, the two types of technologies together certainly starts making more sense, especially if you're compensated for it. But I think ultimately that's the real thing you have to take a look at is, you know, whether it's AC to DC, whether it's located directly at the project site somewhere else, you know, where do you maximize your revenue compensation? And you may end up sacrificing megawatts that get clipped just so you can increase your revenue number. So, you know, it's an exciting time because now storage can be a lot more of a grid asset, and be, you know, be more efficient for the grid, you know, and operationally than strictly just you know, something that's an efficiency for the project.
Thank you very much, John. Let me just take that so that we can all see each other. Thank you very much, John. So now that we've heard the three points of view, and, you know, finally you heard like the financial point of view and, you know, what you should consider when you're thinking about financing these projects, but also securing revenue over the lifetime of your assets, and how it changes in terms of the regulation and the market that you have locally. I'd like to ask a few questions, if I may. There is a few questions from the audience, so I'm going to go to them. I just wanted to ask one in advance because we've talked a lot about AC versus DC, how complicated it is, what you need to calculate. But how about the maintenance or the O&M required for hybrid systems of DC and or AC architecture? Are these different? Are they the same? Should we consider different costs? Wilhelm, I don't know if you want to take this.
So we'll add that.
This is it's an important point to consider as well.
Yes, of course. I mean, if you look at that kind of systems like battery plus storage systems, so storage plus PV systems, the overall time you have to invest for maintenance is relatively low because most of the components are solid state electronics. You would be looking after fans, specifically for when you have containerized batteries, for the rack fans, for the aircon and these things. So all moving parts pretty much. Plus try to check also on the solar system if there's any dirt anywhere, or if any avenues for air are blocked and these things. But that can be done. It doesn't have to be done continuously. So maintenance is relatively low. I'd say the difference between AC and DC coupled systems would be in the DC-DC converter, which is the additional part pretty much. And because you would have so many components of those, so per inverter, you can say you have anywhere between 3 and 6 additional DC-DC converters. And if you have to look after those, and you're talking about systems which easily go above 100 megawatts nowadays, then there is actually a lot to check, right? So I think if there is a difference that should be mentioned here, then it is actually checking on the BCD.
Thank you very much, Wilhelm. Now we have a couple of questions, Sherif, that you've marked that you'd like to answer. So one of them is about the cost of batteries, lifetime operation and maintenance costs, a quite wide question. And the second one was about the maximum reasonable duration for energy shifting time, whether, just below 8 hours with lithium-ion batteries. So they're the first and the second that you've been asked. Just make sure you're mute. Thank you.
Sure. Yeah, happy to help there. The first one is a little bit broad, but it raises up a good point about lifetime cost, which connects heavily to degradation, which is something I always underscore. I wrote an article on LinkedIn about it and another one with Energy Storage News. But as you design your battery project, its use case, the most important thing to look after, I mean, we talked about losses in inverters, we talked about losses in DC-DC converters, 1% here, 2% there. But when you start looking at degradation and how much extremely expensive battery capacity you're losing every year based on the types of cycles you have, the throughput, depth of discharge, average state of charge, all of that, all these 1%, 2%, that goes away, and then you realize you're paying a lot for that degradation. So it just makes sense to optimize the use case. So I like that you mentioned lifetime. There's just too many variations out there to say, like, this is the lifetime cost of ownership of battery systems. What I would advise you to do is to just look at the use case and evaluate, there's a lot of tools out there, evaluate what kind of degradation you will get from every use case using different products, NMC, LFP, even non-lithium products. We're seeing a lot of new kind of long duration systems hit the market. Like I'm very excited by nickel hydrogen technologies like Enervenues. We've been looking at that quite a bit. The characteristics they have shown are quite promising. They're at this point guaranteeing, I think, 20,000 cycles. But again, we mentioned these features at a very high level, like round trip efficiency, self-discharge. You really have to look at the details of these values, because the self-discharge you get at 100% state of charge is very, very different from self-discharge you get at 20% state of charge, and it's very different from 30 degrees Celsius to 20 degrees Celsius. So you have to, the kind of modeling we do for PV systems in PV Syst, we have to mimic that to energy storage, because batteries are the most expensive component in any battery project, and we have to get that right if we want to make successful battery projects. That's a very long answer. I may not have answered your question specifically, but I tried. So
thank you very much. And there was another question, right? The 8 hours.
Yeah. So the limitation we have seen on our side at Duke Energy with longer duration lithium systems has been, for the most part, on the short circuit current capability of the inverters. When you parallel a lot of lithium battery racks together, the short circuit current increases drastically. We have executed a 6-hour system down in Florida, but it took a lot of coordination with the inverter manufacturer, in that case Dynapower, and they kind of they guaranteed that their inverters wouldn't have any issue with the fusing and with that 6-hour duration. But it's not the same for all OEMs. This is something, when you get to that kind of duration, you have to check. You also have to look at the fusing architecture. I know Wärtsilä has their quantum units, and they have their own fusing. So it's either kind of, you make sure these higher durations are good with your inverter OEM, or if you're have a smart integrator like Wärtsilä, checking the fusing architecture on the DC side to make sure it's capable.
Thank you very much, Sherif, for that comprehensive answer to both questions. I have a question here for Wilhelm again. What's the real advantage of grid-connected DC coupled solutions in the UK and in Europe? DC coupling has a lower efficiency than AC. Sorry, this is a long question. This is just moved. When battery energy storage systems just from the grid, the cost of DC converters is still as high as normal battery packs. And the complexity of DC coupling is much higher than AC coupling. The only real advantage would be the marginal saving on transformers, in my view. This is Eduardo's question. So Wilhelm.
Yeah, I understand the point, and I think it's a good question, even though the question itself leaves out the real advantages here. I mean, it's a good list of disadvantages that can occur. I think the answer to this is not every DC coupled system under every circumstance would be the better choice. So what I'm saying here is that the comparisons we've done before, we said a DC coupled system would be 3% more efficient. However, that only is true if all energy would be stored. So what we are seeing here is something in between. Some energy will be supplied directly from solar to the grid, some will be stored. So the efficiency gain we see is somewhere in between 0 to 3%. So if we have a very high ratio of stored energy, then the advantage of the DC coupled system becomes bigger. So this is what we have to look at. The use case has to match the topology we are choosing. And then it can make a lot of sense. It can support our business case. However, the AC coupled systems, because of their direct higher efficiency when you supply directly from solar into the grid, might be the better choice, and that's very true. So the devil's always in the detail. It is about engineering the right system for the right use case, and then DC coupled systems can have an advantage.
Thank you very much, Wilhelm. So Sherif and John, I'd like to see if there is any questions you'd like to answer, because we're out of time, but I think a couple more questions won't hurt us, if you don't mind. But in the meanwhile, I think this is a question more for you, Wilhelm. Someone is asking here about string inverters, and this is something that came to my attention, the other day doing a webinar about string inverters and how that changes the whole architecture of the plant. So maybe you can give us a few words about what happens if you're using string inverters.
Yeah, I mean, that is something Basler is not really looking into because the system started at quite high power of about 10 megawatts. You could theoretically realize that with string inverters, but it becomes very clear that if you're looking into those systems of that size, then the number of inverters you have to use is phenomenal, right? So, and that then inherently provides a problem with MTBF, like the failure rate of components, which then brings us back to that question about maintenance. So that work and that effort certainly would be increased. However, string inverters certainly also have an advantage here because string inverters specifically look after the components they're connected to, right? So if you have a large center inverter, then the large center inverter can only treat the batteries behind it as one battery. The EMS will help here as well, of course, but that's where the other advantage would be for string inverters. But again, also from a financial perspective, it is certainly the more expensive choice to use string inverters.
Thank you very much, Wilhelm. And Sherif, John, have you found any questions that you'd like to answer?
I'll take the question about does it really increase the levelized the IRR really, right? Because I guess the levelized cost of energy really doesn't change too much. But I think the thing to think about is that it's going to be, unless you're in a pure wholesale market, competitive market, and you don't care too much about your offtake and you're willing to take full merchant, I think you're going to have to, in some way, shape, or form, include storage in your project for a whole host of reasons. One is contractually, it may be required. If it is a bilateral, it seems hard for me to believe that a utility is going to not require you to have storage so they could better plan out the timing of when the power hits the grid for themselves. You see that in a lot of these markets. And it also prevents things like the duck curve from happening. The other thing that you can think about too is that as people become more accepting in the capacity markets that exist, having storage will certainly help out there to give you kind of a higher overall credit. And then finally, as you think about where you put your project, the idea that you're going to get some curtailment is certainly going to be present, and you're going to get curtailed to a large degree, especially as things really start to expand in the world of renewables, whether it's wind or solar. So the thought of putting a battery inside your project will certainly increase your IRR, because what always shocks me is that people think that they have a great idea and they don't want to tell anyone about it. When the reality is that your great idea is probably shared by about 50 other people, and if it isn't, by the time you do it the first time, everyone will know about it and will flood to whatever your great idea is. So there'll always be an overbuild situation as long as one an opportunity presents itself. So by putting a storage project there, it will certainly increase your IRR as you build out, as people kind of exploit either the same strategy or the location that you have your project.
Thank you very much, John, for putting like some truth in there, because for sure, we hear that a lot in our line of work. Everyone is like, oh yeah, this is completely confidential. And what we're seeing is actually most people are kind of like drifting around the same areas. So question for Sherif and Wilhelm, if you have any other questions you'd like to answer, so you will go next. Can you please elaborate more on how to define the optimal sizing of battery energy storage system to capture the PV clipped energy?
Sure, absolutely. I think for this one, I can share my screen if that's okay.
Yeah, go for it.
All right. So if you see my screen here.
Yeah,
right?
we see it. It's fine. Yeah.
To answer that exact question for us as we were getting ready as we were designing a project probably 3 years ago, it's now being commissioned. These are kind of calculations we did. Right now, this is just the output, right? The back end is extremely complex and involved, simulating hundreds of cases. But at the end, the main parameters were, what is the DC-AC ratio, or otherwise called overbuild capacity of your solar system? And what will be your battery system capacity, right? And when do you start to get diminishing returns as you get, to higher DC-AC ratios, or as you go from one battery sizing to the other? So as you can see between the lines here, when I go from this orange line to this gray line, and then from this gray line to this yellow line, it's actually the distance between them starts to reduce, which means you get, every time you're adding battery capacity, you're getting less extra energy from the solar. So where the optimal point usually lies is at the inflection point, which is kind of when you start to see an inclination in the line, and just, the more capacity you add, the less gain you have. So when you double your capacity, you only get 150% more energy. So that's where the question line, the answer would lie. Now, the complexity of it is that there's just a lot of parameters involved. So you have your battery power, you have your battery duration, you have your solar DC capacity, you have your solar AC capacity. So you put all that together, right? You get a lot of combinations. But once you run them all with the irradiance of the region you have, you can use PVSYST or just get a TMY3 file from for your region. You'll be able to find kind of where you start to get diminishing returns and find the optimal point for your project. I hope that helped.
Thank you very much, Sherif. Handing again, going back to here and explaining this again, how it applies to the question. Thank you. And just to finalize, because I'm very mindful of time and I know people have to leave. Wilhelm, your last question, did you want to answer? I think you don't have that many left now.
Yeah, I accidentally actually clicked the wrong button when I said it has been answered live already. So I don't want to hide any questions here. And there was one about the response time. But the question around the response time has been with regards to UK rules. The question was, do DC coupled systems respond fast enough according to the UK rules? I personally don't know how fast they have to respond, but I can tell that DC coupled systems clearly respond equal or faster than 1 second. So if that is enough for UK systems, then it would fulfill it. I can also tell that response times are being improved, because it's a combination of response times from the software, the DC-DC converter, and the inverters. So all associated parties here are improving their products to make that response time much faster. So below 1 second, and very soon, actually much faster.
Thank you ever so much, guys. This has been a really interesting webinar. It's the first time. Yeah, go on, Sherif.
I'm very sorry. There's just a very good question that I like to answer. Is that okay if I take one?
Yeah, go on. I love this because you're all such nerds. You love this stuff, and I'm learning so much. So go for it.
Awesome. I appreciate it. All right. So yeah, so the question on degradation, and I think someone seconded the question right now, but the question on what is the average degradation per year, an estimate, right? And I appreciate that question very much, because that's what a lot of people are doing. They're saying, all right, what is the average degradation of a battery system per year? And truthfully, the answer is you should never assume that there is an average degradation per year, because it depends on the use case, it depends on the throughput, it depends on the battery type and the OEM. So this is kind of a software I use to kind of deduce that degradation. What we do is we input the profile, and what it does is it's kind of like PVSYST. It analyzes the profile and looks at the battery product you selected, like the CATL, BYD, or if it's like another energy storage technology, and it tells you, all right, what kind of percentage degradation per year you would expect. And once you have that, now I know, like for this simulation, I know I'm going to get down to 85% by year 20, which means if I want to overbuild this project, now I know I have to plan on getting to 85% in 20 years. So I calculate what my starting kind of capacity needs to be and go from there. So, be concise, just never assume it's going to be a constant rate based on a previous project. Every project has its own rate of degradation based on the profile. And thank you for allowing me that time.
Thank you very much, Sherif. I think it was worth also pointing that out, and I think it's still very unclear how you modeled, the batteries, and especially in regards to degradation. So I think in the future I hope to get a little bit more clarity on this, because this is a question that we get a lot. So maybe for the next webinar. But for now, I'd just like to thank you so much, Sherif, John, and Wilhelm. You're such superstars. Thank you so much. And I will see you three, and also all of the people in the audience, hopefully in the next webinar. So thank you very much, and see you next time. Thank you. Bye.